Okay, let's start. So in the last class and the class before that, we were discussing control sources and control sources from the perspective of their impedances, right? So we saw that, we explored few of them. So the most obvious one is a voltage control current source, which is nothing but a MOSFET when the input terminals are between the gate and the source, and the output terminals, incrementally I'm talking about, are between the drain and the source, right? Why? Because firstly, there is when you have a control source, there has to be an input to output relationship, which anyway a transistor has between the gate and the source and the drain and the source. But in this case, from the perspective of impedances, the looking in impedance in case of a transistor, if the input is applied between the gate and the source, that is Rin, this is almost, this is infinity, not almost. In the model that we have taken, it's infinity. Even between the drain and the source, the output resistance is infinity, right? So that satisfies the conditions of voltage control current source. And then we saw that if we want to have a voltage control voltage source, again, the controlling terminals are the gate and the between the gate and the source, because Rin is infinity, and that is the input port anyhow. But the output terminal in this case is what? In a voltage control voltage source, what is the expected output impedance? 0, right? So if you transistor has 3 terminals, so looking into which terminal the impedance is not infinity, for example, in this case, ideal cases. So looking into the gate, it is infinity. Looking into the drain, infinity. Looking into the source, 1 over GM, right? Looking into the source is 1 over GM. Now depending upon GM is a user control variable, designer control variable rather. So if you want the transistor to behave like a voltage source, then all you have to ensure is 1 over GM is tends to 0. 0 is not possible, but 1 over GM is much lesser than the load that is driving. Then it becomes a voltage control voltage source, right? So essentially your input can be between the gate and the source, and the output is between the source and some referred ground. That ground can be incremental, the ground can be something else, right? So this Rin is 1 over GM. Okay, so this can be used as a voltage control voltage source. By the way, in this case, the drain is the way we had we had structured. The drain was incrementally grounded, right? It was a common drain amplifier, if you recall, right? So the configuration that we had, these are single transistor configurations. These are common drain, and even though one might argue that it should not be an amplifier because it doesn't give you a voltage gain of more than 1, but an argument can be made that it gives you a power gain, because essentially the input power is what? How much power is going into the transistor from the input side? 0. But at the output side, if you connect a load resistor, it is drawing in some current, right? So you are developing a voltage across a load resistor, which means you are drawing in some current, which means there is an output power. So the power that is going into the transistor is 0, but you are, from the perspective of the source, but from the perspective of the load, you are able to deliver some power, which means there is a power gain. And one might say the power gain is infinite, right? Input power is 0 from the load, but output power is infinite. Output power is non-zero, which means the ratio is infinite. So is there a fallacy there? How are we getting that infinite power gain? Yes, it is the incremental domain, not an absolute domain. So in an absolute domain, where from, so now if I say that from where that extra power at the output is coming, or actually do you have an extra power? As you pointed out, it's in the incremental domain, which is correct. The question is, the input power is 0. right? So I take the, let's say I take the total input power. Total input power is 0 because no current goes into the gate. And if there is a load connected, you develop a voltage across it, right? So the total output power is non-zero. So this power that is getting delivered to the load, assume this is connected. So this P out, this is RL, it's V naught square over RL. Average of V naught square over RL, right? So output power is non-zero. So from where is the extra power coming? Yeah, there is a source. There is a source connected, right? That is the first couple of lectures that we had, right? So there is a source connected, but the source is connected at DC. So this nonlinear element is able to convert the DC voltage into an AC or a voltage at a different frequency, right? And when we say there is a power gain, we are talking about power at that particular frequency, right? So the power the power that is being carried through a signal of a particular frequency at the input is 0, but that frequency signal has a non-zero power at the output. From where did it get that power? From the source. The source was at DC, but the nonlinear operation converted that DC power into a non-zero signal frequency. Anyhow, I mean, that's not the point of discussion for today's class. Just wanted to remind you that there is a source which is pulling all the strings in the background. Okay. So this is a VCVS. Then we also saw a current controlled current source. By the way, when will you use a VCVS? I mean, what is the use case of a VCVS? What situation might arise in which you want to use a VCVS?
Want to try some resistor in the voltage, but connecting it directly from the voltage.
Yeah, exactly, right? Perfect. So if you normally we have, let's say I have one stage somewhere which has some Thevenin output voltage, Thevenin output impedances, right? And I can model that stage as V Thevenin and R Thevenin. This is one stage. And maybe I want to drive another stage which has an effective input impedance of, I don't know, maybe R in 2. Okay, so this output voltage is open circuited, and if I connect these two directly, then naturally the open circuit voltage will drop, right? And for some reason, if the application demands, I don't want that drop. Then I have to connect a voltage control voltage source. And what is a voltage control voltage source? Simplest configuration of gain of unity is this guy that we have just seen. And you bias it and all those things you do, AC couple and all sorts of things that we know we do, right? So this is one typical application of a voltage control voltage source. So the other thing that we did was a current controlled current source. By the way, this is also called a voltage buffer that we had referred to in one of the previous lectures. So the other thing that we did was a current control current source, right? So in a current control current source, again, using a single transistor, what is the expected input impedance of a current control current source? 0. So where would you connect the input? At the source, right? So it's at least not infinite. That's good. So Rin is 1 over GM. And you can take the output. The only place you can take the output when the source is occupied is the drain, right? So this R out is infinite. And you obviously bias that gate. Incrementally, the gate is shorted. And again, what is the use case for a current control current source? Why would you want to use a current control current source? This, by the way, is also called a current buffer. Why would you want to use a current control current source or a current buffer? I mean, think of any scenario where you might want to use. Anything. Yeah, exactly, right. You don't want the current to be divided between its current source will have some internal resistance, right? So you don't want the current to be divided between the current source of the internal resistance and the load that you are planning to drive. Right? For example, let's say I have a current source and it has its own internal resistance. Let's say I call this RCO, current source output resistance. And you want it, and this is ISC, so short circuit current, and you want this guy to go into an RL. And for some reason, you know that RL is much greater than RCO. Right? So let's say assume that RCO is, I don't know, maybe 10 kilo ohm, and RL becomes 100 kilo ohm. Let's assume this is the case. So if I simply connect this, so will majority of ISC flow into RL or will it flow into RCO? It will flow into RCO. And let's say you don't want that to happen, right? You don't want that to happen. The situation demands that you don't want this to happen. Then you have to put a current buffer, right? So just like a voltage buffer buffers the voltage, right? It takes the voltage from one terminal and transfers it to another terminal without any attenuation. A current buffer should be able to take in the current and transfer it to the load without any attenuation, right? So you have to put a contraption here, which is a current control current source. So in this case, the current control current source can be, for example, incrementally at least, I can connect this to here, and that RL can go and get connected here. Right? So if this input impedance that is 1 over GM, for example, in this case is approximately 1K, then ISC will flow into the transistor and not into its own output impedance. Right? And once it flows in, it has to flow out from the other side. There is nowhere else to go. Right? It will, yeah. Yeah, so this question is how is R out infinity? So do you agree with the fact that here the R out is infinity, the first case? No? Okay, so then you should have stopped me then. So let's explore this then. So what is the impedance between this incrementally? That's the question. So how would I go about finding this? Incrementally, the gate goes to ground, gate to source goes to ground. I apply a test voltage here. What is this? GM times? What is VGS? 0, right? Gate voltage is 0, source voltage is 0. So GM times 0. So this goes off. What is the current? 0. Then what is the impedance? Infinity. Right? Make sense? But then one might argue that a transistor is a symmetric device. A MOSFET is a symmetric device, right? If you just look at the cross-section of a MOSFET, you cannot make out which is drain, which is source. Then how come looking into the drain, you have an impedance of infinite, and looking into the source, you have an impedance of 1 over GM? Yes, the way is biased, but that is correct, the way it's biased. But what about the biasing that it's making this effect? Looks like it's quite a drastic difference, right? One, I can assume it to be open circuit. Pardon? Direction of the quiescent current flow, again, it's correct. I mean, in the sense that direction of the quiescent current flow decides which is drain, which is source. But what is the physics behind the fact that So the question is, what is the physics behind the fact that I change the voltage at one end, current changes, and other change the voltage at other end, current doesn't change. That has to do with the charge distribution. Once you have a pinch off, right? If you recall the pinch off phenomena, there is no channel at the drain. The channel has vanished. So if I change the drain voltage, there is not able to affect anything. It's not having any effect on the charge distribution in the channel. If you don't have any effect on the charge distribution, there is no way you can change the current. But there is channel, significant amount of channel, almost the entirety, I mean, significant part of the charge lies at the source junction. So if you change the voltage there, you are able to change the charge, and hence you are able to change the current. Right? So in a way, the physics behind it also supports why at one end you should see an infinite impedance or very high impedance, and other end, I mean, depending upon how you bias your transistor, the impedance can be quite low. Okay. Okay, fine. So this is vitally important to understand that, or at least remember at this stage of the course, that looking into the drain, you have very high impedance. Looking into the source, you have very low impedance. Okay. Okay, fine. So now why am I harping on these things? The reason I'm harping on these things is the model of the transistor that we have taken is a very simplistic model. That is not a very practical model which can be used everywhere. It can be used in many places, but not everywhere. Yes. This is an incremental, right? Okay, right. Okay.
So, corresponding in the person diagram, what do we have?
Yes. So, well, all this is attributing to the transistor is bias in saturation, right? So, which means that there is a voltage that has developed between VGS. If the transistor is not on, there is no point in dealing with saturation.
That is okay, but if we are applying the VGS at the drain, then the other two terminals are getting grounded. I'm asking why is that?
Okay. Okay. So I'm not sure I understand the question. Let me rephrase and tell me whether this is what you are asking. So you are saying that if I connect what if I connect the VTest to only the drain? Is that what you're asking?
That is what it is.
Yes. So let's see. So if I connect this to drain, so what about the source? Yeah, so something is connected to the source. It can be a current source, which in the quiescent model, it can be a current source, it can be a resistor. Something is connected, right? So let's assume something is connected. Let me connect a resistor. I mean, I just make resistor to be infinite for if it's a current source, right? So let's assume that it's a resistor. So what about the gate? Gate is biased with something in the quiescent model. Right, has to be, right? I mean, through a resistor or something, it has to be biased, right? So let's assume it's biased to a resistor, maybe. So this is also goes to ground, correct? So far, it's okay. Okay, so connect all the grounds. Okay, so gate voltage is 0. We are okay with that?
What if there was a current source at the source?
What if there was a current source at the source? Okay, fine. So then this opens up. Fine. Okay. Gate voltage is still 0. Okay. What about the source voltage? Let's see. So it's GM 0 minus, let's say, VS. Right? So if I do a KCL at VS, what do I get? GM VS is 0. So VS is 0.
No matter what the other conditions are, it will always have to be basically grounded.
It's not grounded, right? This is not grounded. So this is not absolute ground, right? So moment I say it's not an absolute ground, what are the type of grounds you know? Right? Why is this a virtual ground? It's simply a virtual short. Because if this guy gate changes, the source also moves along with it. It's almost like they are tied together, but it's not an actual ground. Yes.
Can you say that if the voltage at G is VG, then VS will necessarily be VG?
Yeah, right. So if the voltage at gate, as you rightly pointed out, not in this particular scenario, but in a generic scenario, if this configuration exists and the gate moves, the source also has to move in tandem with it. So it's almost like they're shorted. They're virtually shorted. They're not shorted through and where, right? They're virtually shorted. So that's why in this configuration that we see voltage control voltage source configuration that we see, you saw that the difference between the gate and the source, that was the error voltage that we were doing, was tending to zero when something was going to infinity, like GMR was going to infinity. So that is, this essentially can be thought of as an op-amp where negative feedback has been established, but I don't want to get into that at this stage of the course. We'll get to that later. Right? Simple circuits has all the knowledge that is necessary to understand the course. Okay. Fine. So do we? I mean, is there any confusion as to why looking into the drain you have infinite resistance? Okay. So at least we know that looking into the drain, you have very large resistance, infinite resistance, at least with the model that we have. And looking into the source, we have very small resistance, or we can make it small depending upon the requirements. If I want small, then small and large are relative terms, small with respect to something. If I know whatever is that thing, then I can design GM in such a way that I can make the input impedance smaller than that. Okay, fine. So now the next thing that I would like to go into. So by the way, I haven't yet done CCVS. We'll do CCVS for a later date. So I'm not touching CCVS right now. The thing that I wanted to touch upon is the fact that the model of the transistor that we have taken till now is extremely simplistic one. In the sense, it has only one GM, right? One voltage control current source, and that's all has been our transistor model till now. But that is not a very accurate model, even for first principles operation. In most cases, in some cases that is fine, but in most cases it is not. And the reason it is not is because of this. So if I go back to the charge distribution in a cross section of a MOSFET, so it's a drain, source, gate, and let's assume that it is biased in saturation and all those things. So this is an N MOSFET. So this is P. So you have electrons which have developed in the channel. These are mobile electrons which have developed in the channel, and there is we have pinch off, right? We have pinch off at this region. So just at the edge of saturation. So now if you recall, we argued that if I increase the drain to source voltage, right? If I keep on increasing the drain to source voltage, this triangular distribution of charge will not really change, right? That's why the current was becoming constant. But there was a question when I discussed this, that where will that extra drop happen, right? So the circuit hasn't changed. I have just increased the voltage, right? So let's say this is biased at some quiescent VDSQ, and I increase the voltage. So where will that extra drop get? Where from will you get the extra drop? One might argue that extra drop happens between the drain and the source because it's a current source. I can keep on increasing the voltage, the current will not change. That argument is valid. But now if I strip open the device and look into it, and I say that this device is now, I know that these are sections of small MOS transistors put one after another. Where will that extra voltage drop? Pardon? In mobile charges, but if I actually further make your assumption that the mobile charges, the drop is not significant because that is immobile charges, right? Okay. Okay, immobile, except immobile. Sorry. So let's say, so there are a bunch of immobile charges here, and if I keep on increasing the drain or voltage, what will happen to this channel? This channel will try to move to the left, slightly to the left. But moment it moves to the left, you are exposing the immobile charges, and immobile charges give you a lot of resistance. So the extra drop will occur across that small sliver that will get exposed. Okay. All these things are not important. The important thing to note here is that if I keep on increasing drain to source voltage, there is a second order effect from this channel slightly moving to the left. There is a shortening of channel that can happen, right? Not a first order effect, it's a second order effect, but there is a shortening of channel that can happen. from whatever we have discussed till now, what do you think will be the effect in the current? Current has been saturated, but will that saturation current change slightly or no? Resistance is present, just as the current was not dropping across that resistance. That incremental resistance will cause a drop of that incremental voltage. But we agree with the fact that, one second, we agree with the fact, I'm exaggerating the picture now. I agree with the fact that this can happen, right? So this guy has an extra resistance, but it's okay that extra voltage drops across the resistance, that I agree. But because there's a shortening of channel, do you think something can happen? Yes.
Mobile charges will still remain the same. So current.
How do you say that mobile charges is going to remain the same? I haven't said anything about say, I mean, whether it's going to remain the same or not. It might remain the same, might not. I don't know. Because the profile seems to be changing. But let's say it has only changed slightly. I have exaggerated the picture. In that case, the assumption can be the mobile charges is approximately the same, right? So think about the length. Can I say that the length has shortened? Length of the channel effectively has shortened, right? So from, again, very preliminary equations that we already know. If the length reduces, what happens to the current? It increases, right? So effectively the current starts to increase. Right? So more you increase the drain to source voltage, the current is not, it doesn't keep saturated, it doesn't keep constant, it slightly increases. It keeps on increasing. It's an imperfect current source. Okay, so then we can do the math. All we can then say is that we know that IDS, yes. Okay, so there are no mobile charges in this. If I understand your question is there is no mobile charges here, right? How is the current flowing? So the reason the current is flowing, think of in terms of electricity or the same type of, or the type of charges that exist. So this is equivalent to the situation where, let's say you have whole bunch of electrons, mobile electrons here, a set of immobile charges, which is Na minus fixed charges. And you again, you are taking this stuff out, right? Okay, so this is also N plus. This is also a whole bunch of electrons. So there are 3 slabs connected next to each other, not in the way I have represented, but assume that you have a slab of electrons. Between that sandwich, there is a slab of mobile charges, right? So now if you apply an electric field here, if you apply an electric field in this direction, do you think the electrons will flow through that immobile region? It's not a PN junction there. It's not a PN junction, right? It's not a reverse bias PN junction between those 3 areas. So you have negative potential, you have electrons, it will flow. Because the electric field will drag it out. There is nothing that is opposing its flow. Right? It's not a reverse bias PN junction. Had it been a reverse bias PN junction, it wouldn't have flow. Right? So, for example, this side is reverse bias PN junction. So electrons don't flow into the body. But that side, even though you don't have, so that immobile charge region is not generating any charge, but it's not blocking any charge to flow through it. It's a passive. Okay. Okay. Yes.
So I can keep applying voltage across DS and the current.
It keeps on working. Yes.
But then there's a side increase.
Yeah.
So there's no upper limit to it.
Okay. So in principle, in all devices, there is an upper limit, there is a breakdown limit. So what generally tends to happen is that, that's a very good question. So if you take device classes, what you see is that to keep on doing this, right? I don't say don't give any upper limit. This channel will keep on coming all over here and get punched through. It's called the channel is zapped totally. So it's almost like there is, I mean, you don't need any inversion because you have applied so much of voltage, right? I mean, then the charges can flow directly from drain to source. It's almost like a breakdown of a capacitor, not in this context. But you have a dielectric, if the dielectric breaks down, then it doesn't behave like a dielectric anymore, right? The current simply punches through. But that's, I'm just giving you an analogy. That is not exactly the phenomenon here, because the capacitance is between these two terminals, not here. right? But I mean, something similar can happen. And there can be other things also. There can be a case in which this reverse bias junction can also start conducting. Have you heard of this avalanche breakdown? Right. So there can be, if you keep on increasing the voltage. So what generally tends to happen, again, I'm going to divide this. So for every bond that breaks, the electron and the hole pair that comes out with a certain amount of energy. And if the energy is process a critical energy, then it can go and break another bond. So the probability, if you do this, this is like an infinite series, right? One goes and hits another one goes and hits another one. So if the infinite series diverges, then you can say there is a breakdown, right? So then it becomes avalanche breakdown or something like that. So in this case, also something similar happens. But I mean, obviously, as a circuit designer, you don't want to operate in that domain. So one of the reasons, that's why you see that as these dimensions of the devices get smaller, right? So earlier, this channel length used to be, when the technologies came out, it was like 1 micron, then it became 500 nano, 180 nano. Now people operate at 3 nanometers. So as the technology has shrunk, which means the dimensions have shrunk, so the operating voltage also has shrunk. Just to honor the fact that you don't want the devices to get broken up, right? Because the electric field, ultimately everything is electric field, right? If the electric field becomes very large, then the devices can reach breakdown. Okay, so that's why these voltages, many of these devices now operate at like 0.8 volts. That is the maximum you can go. Okay. Okay. Again, this was a digression, but very good question. Okay, so now if I again go back to the simplified current voltage equations that we had in saturation, this becomes so this L, I will write it as L effective because it's not a physical L anymore. Because things like if I increase density source, the effective channel can move slightly. Okay, so this L effective, if I call this as delta L, this L effective can be written as L minus delta L. Okay, so I write this in the form of delta L 1 minus delta L over L. So you know, whenever somebody writes it like this, what's going to come? I'm going to do some Taylor series, right? So sorry, this is L. So now I'll take this 1 minus delta L to the numerator. This becomes approximately 1 plus delta L over L. Okay. So, and as it turns out, again, I am not going to get into the physics behind it, but you can show that this delta L, the amount of decrease of the channel, and in an incremental perspective, is also dependent on how much increment of VDS you had, right? So you hit saturation and then you incremented VDS. So delta L is also, one might stand to argue that delta L is proportional to that incremental VDS. Okay, so in that case, I can say that delta L is proportional to delta VDS. This is on top of saturation edge. Okay. So that's what people generally tend to do, is to say that since L is a property of the device and delta L is proportional to VDS, I will say that delta L over L is proportional to VDS, and I will assign a proportionality constant, right? So what we tend to do is to say that delta L over L is proportional to VDS. L is a constant anyhow, and we say that delta L over L is equal to some lambda times delta VDS. Okay, a lambda n, because we are talking about a NMOS device. So our IDS equation gets modified to delta VDS, where delta lambda 1 plus lambda n times delta VDS, where delta VDS I can write it as VDS minus VDS sat. Right? Where the VDS sat is that value for which we had just hit saturation. Okay, so this is, I can say that VDS sat is V overdrive effectively. Okay. Okay, fine. So what is the effect of, what is the impact of this guy? What is the impact of this into our current voltage graphs? What is the impact? So again, question is, this whatever modeling, I mean, division of model that we are doing, it is effective for our saturation region of operation or linear region of operation also. It's only saturation. In linear, there is no concept of pinch off, right? So we can stick to the old model. So linear model doesn't change. Linear model is as is. So when we are plotting the IDS versus VDS plot, earlier the model was something like this, and then it was flat. So right now, in the linear region, till V overdrive, nothing is going to change. We haven't touched that model. But what's going to happen after V overdrive? It will now start to increase, right? It will now start to increase. Now this slope, whatever is the slope, what does it signify? Or the inverse of the slope, what does it signify? Yeah, it's the incremental resistance of the current source. Earlier, the current source was an ideal current source, right? Earlier, the current source was an ideal current source where we had only a GM, VGS and nothing. Y22 was 0. But looks like now your Y22 is not 0. So there is some extra term that is going to come in, or an extra component that is going to come into the model. Okay. Questions? I see some confusion in the class. I can address the confusion right away, or it might build up then otherwise. No confusion? Okay, good. Okay, fine. So now the question is, I mean, obviously we are dealing from whatever the course has gone till now, you understand that we want everything in terms of incremental, right? So we like to figure out how does this affect our incremental models, right? So before we go to the incremental model, if one more piece of information, and that is, you will see that this particular relationship is not very common in the literature. I will tell you what is common in the literature, and I will also tell you the reason behind it. In the literature, what we'll tend to see is this model. IDS is times 1 plus lambda n VDS. Mostly you don't see that minus VD sat times lambda n. That is often dropped. And that is, even though that is not a particularly physics specs correct model, but that is a model which can be used with a lot of accuracy also. The reason is, normally this VOV, this region is much smaller than this region. So it's almost equivalent to when you are calculating the total current with some amount of accuracy, you can drop that last minus VD sat term and still get reasonably accurate current. Right? So algebra becomes much simpler if I drop the second term. I mean, 1 minus lambda, that minus lambda VD sat term. Okay, so because the algebra becomes simpler, we say forget about it. We'll not bother about it, right? So we are not trying to, anyhow, all these equations are, none of them are truly correct. I mean, each transistor model, actually, if you are pursuing a career in modeling a transistor, then you will see that the compact model for this has probably 100 parameters. So none of these are, will be able to model the IV characteristics to nth order of accuracy. So the trade-off is always between, do I want a very accurate model and get bogged down into algebra, or can I get the amount of information that I require, can I extract it from a very simplistic model, which is easy to intuit, and then work along with it, right? So if some parameter doesn't add too much value, we tend to drop it, right? For circuit designers, not for device designers. It's the other way around for the device designers. You want to model the device to a very accurate, to the extent that you can, because ultimately when you are simulating and you are fabricating a device, you would want to ensure that its current voltage characteristics are very accurate, right? So there are two aspects to it. So in a circuit designer's mind, make it simpler, so that I can design some things with it, right? If it's not very simple, then probably design is not very intuitive. Okay, so in this course also, we will be using this model. Okay. Okay, fine. Pardon? Current in the linear region was that equation remains as is, right? So that hasn't changed. So this becomes current in the linear region was mu n C ox W over L VGS minus threshold voltage times VDS minus half VDS squared. So this remains as is. The question being, you had a question on this? Okay. Okay, fine. So now, since the current the linear region equations haven't changed, the model for the linear region also hasn't changed. But clearly, the model for the saturation region, the transistor model for the saturation region has changed. Okay, so let's see how has it changed. So there are again the two-port model of a transistor: Y11, Y12, Y21, Y22. So Y11, do you think it has changed? No, Y11 remains 0. Y12, Y21, which was the GM. I think I should write it this way because Y21, which was the GM. So that equation seems to have changed, right? So what will be the GM in this case? So GM is del IDS, del VGS, which is VGS is embedded inside the overdrive. So mu n C ox W over L VGS minus threshold voltage 1 plus lambda n VDS. Okay, so but again, I will see that this theme will appear multiple times. If this slope, if this slope is not significant, now whatever is significant has to be defined later on. If this slope is not significant, then I can say that IDS to a first order is equal to the IDS at the edge of saturation, right? If the slope is very large, then that approximation is not valid. But if I want the transistor to operate as an amplifier, would you expect the transistor to have a very shallow slope, or ideally the characteristic slope to be very steep or very shallow? It want to be shallow. It's very steep, it's a useless transistor anyhow. There's no point wasting time on it, right? So it is expected that it is supposed to be shallow. It is expected that the transistor, whoever is fabricating the transistor, will give us a characteristic which is shallow. We cannot expect it to be 0, but it has to be shallow. If it is shallow, then as long as lambda n times VDS is much less than 1, I can drop that lambda n VDS. Okay, so as long as, so if lambda n VDS is much less than 1, then GM equation remains the same. Right? Even IDS equation remains the same. Now I can see some of the questions, and if it remains the same, why are we spending time on this, right? You will see why we are spending time on this. So let's focus to Y22. Right? So this will give you the answer. So what will be the Y22? Y22 was 0 earlier. But do you think Y22 will be 0 now? Right? So we'll differentiate IDS with respect to VDS. So when we differentiate IDS with respect to VDS, what do we get? Yeah, so mu n C ox W by L V overdrive square times lambda n. Right? So this is the reason why we cannot neglect that term, because you can neglect something with respect to 1, but you cannot neglect anything with respect to 0. Right? So if Y22 were 0 and Y22 were non-zero, the ratio of the difference is infinite, right? So you cannot neglect anything with respect to 0. Okay. So the whole purpose of this discussion is is the fact that firstly, the transistor equations are not fully accurate, but to the extent that we can assume they are accurate, we can, for calculating quiescent current, for calculating GM, I can still keep on using the old equation. But for calculating Y22, I cannot. Right? For Y22, I need that extra factor, that lambda n term will come. Okay. Okay, fine. So now, so there is a term for this. This, just like Y21 we call is GM, this is called GDS. It's the conductance between the drain and the source. Okay. So our old transistor incremental model was this. So this was the old incremental model. So this was gate, this is source, this is drain, this is GM times VGS. So the new incremental model becomes, this remains as is. This is GM times VGS. But now I have a Y22, right? And that Y22 will appear between the drain and the source. And this is GDS. Again, I'm sketching in terms of conductance. The actual resistance is 1 over GDS or RDS, right? So where GDS is lambda n times that, lambda n times half mu n Cox W over L P over drive squared, which this guy can be approximated as an IDS, right? So this becomes lambda n times IDS, approximately. Okay, so the transistor has an output impedance, right? So far we have been ignoring it, but in principle, the transistor has an output impedance of value 1 over lambda n times IDS. Okay. Okay, fine. So as you see that, I mean, this is the fun part of circuits, right? Once you know about some basic topologies and the model change, you need not go back to the first principles again, right? You can basically use the same model and add in construction. So what I would request you to do is go back to probably like tutorial 1 or 2, where we had a lot of small signal models, right? There was, I think, tutorial 1, maybe I was asking you to, pardon? Yeah, first one. So there, see that whether when you, for every GM that you have, for every YP1 you have, you put in a GDS in parallel to it or resistance in parallel to it, you see those configurations now look familiar or not. Right? Go back and have a look at those. We'll use some of those results. I'll prove them, but I'll use some of the results of tutorial 1 in the next class. Okay. Okay, we'll stop here.